Now we need to discuss a certain simplicial map, which I'm going to call mu. Okay, so in context again, we've got a abstract simplicial complex K and its barycentric subdivision K prime. And as we've discussed previously, there's this homeomorphism beta from mod K prime to mod K, and inverse going in the opposite direction. But neither of these is actually a simplicial map. They don't come from maps of abstract simplicial complexes from K prime to K or from K to K prime. But if we look in the direction, the beta direction, okay, we've got a map from we've got beta as a homeomorphism from mod K prime to mod K, and it's not the same as the realization of a simplicial map mu, but it is closely related to that. So we're going to need to define this map mu. Okay, so for this, we let K be an abstract simplicial complex, and we need to choose an ordering of the full list of vertices. Okay, so you've got vertices v1 up to vm. We're going to choose an order. And so now if we've got some simplex sigma, so that's a subset of the vertices, and we can write it as vi0 up to vir with the indices in increasing order like this. So once we've done that, it's meaningful to talk about the last vertex, which will be this vir. Okay, so we're going to call that last sigma. And essentially the same thing, but slightly different notation. I mean, for this simplex sigma, it gives us a vertex sigma hat in the barycentric subdivision K prime. So we can define mu from the vertices of K prime to the vertices of K by sending the vertex sigma hat of K prime just to the last vertex of sigma. So let's look at a picture in the case where K is just the boundary of a triangle. Okay, so here's your K here with 3 vertices 0, 1 and 2. Here's your K prime where each of these edges has been split into 2, and our mu goes like this. So if you look at 0, 2, that gets to the last vertex in 0, 2, which is 2, and the 1, 2 hat, that also goes to the 2, and the 2 hat, that also goes to the 2. So these kind of half edges here, they all get squashed down up to this single point here, the vertex 2. Similarly, this here you've got this vertex that's 0, 1 hat, and the last vertex in that is 1, so the 0, 1 hat gets sent to 1, and this 1 hat also gets sent to 1. So this blue edge here, this blue half edge along the bottom, that gets squashed down to this single point here. And then this edge here gets stretched out to cover that edge of the triangle. This edge here gets stretched out to there. This edge here gets stretched out to here. So that's the effect of your of the map mu in this case. And you should be able to see that that's actually kind of a homotopy equivalence. We've just taken this kind of arc here between the 0, 2 hat and the 1, 2 hat, and we squashed that down to a point. And we squashed that down to a point, but because those are just intervals, they're contractible anyway. It doesn't really change the homotopy type to squash those down. And so let's look at a more complicated example. Here's a bigger simplicial complex K. Here's its barycentric subdivision K prime, where each of the original triangles has been divided into 6. Okay, and the effect of the map mu is like this. Each of the vertices in the subdivision gets pushed down to one of the vertices in the original complex. And you can by doing the slider, we're seeing the kind of homotopy between. This is a picture of the geometric realization of K prime essentially, whereas this is a picture of the geometric realization of K. And this kind of original picture is showing you the effect of the map beta, which gives us a homeomorphism from the realization of K prime to the realization of K. And this picture is showing the effect of mod mu, which is another map from the realization of K prime to the realization of K that's no longer a homeomorphism. And you see that these kind of pinky triangles here, they all get squashed down to a single point. These purpley triangles here, each of those gets stretched out to cover a whole edge. And these green triangles, there's one in every 6 of these triangles is green, and these little green triangles get stretched out to cover a a full 2-simplex of the original complex K. Okay, so there's a connection between this this mu and the idea of direct simplicial approximation that we discussed earlier. So let's recall how that goes. Okay, so for any vertex u in a complex L, we write the open star to be the set of points x in the geometric realization of L for which there's a strictly positive coefficient of u. And we say that a map F from the vertices of L to the vertices of M is a direct simplicial approximation for a continuous map P if P sends the open star of U to the open star into the open star of F of U for every vertex U. Okay, so if the original definition of a direct simplicial approximation is a little bit different. That was given in definition 19.9, but we proved at lemma 19.14 that the original definition was equivalent to this condition that we've written here. So the point that we want to make now is that this map mu is a direct simplicial approximation for the continuous map beta. Right? So context for direct simplicial approximation, you've got a map between geometric realizations, which isn't necessarily a simplicial map, but you want to approximate it in some sense by a simplicial map. Okay, so this beta here is not a simplicial map, but it's well approximated by this map mu. And notice, we proved in section 19 that if you've got a direct simplicial approximation, then it is actually a morphism of simplicial complexes automatically. So that's another thing we can conclude here. And also from the results in section 19, it's automatic from this fact that the realization of mu is homotopic to beta, and from that we can easily see that the realization of mu is a homotopic equivalence. Okay, so we want to prove that this is a direct simplicial approximation. Okay, so we need so that's definition says we've got to do something about the open stars of all vertices of K prime. So remember, the vertex of K prime has the form sigma hat, where sigma is a simplex of K, we can assume that these simplices are listed in increasing order, so that the mu of sigma hat, that's the last vertex of sigma, so that's going to be Vd. Okay, so now the condition is we have to check that beta is sending the open star of sigma hat into the open star of mu sigma hat. Okay, so let's look at some point in the open star of sigma hat. We need to show, like I say, that the beta of it is in the open star of mu sigma hat in K. So what does it mean to say that x is in this open star? It means that x has has a term t times sigma hat with t strictly positive. And so when we do beta, remember what we do with beta, we send sigma hat to the barycenter of sigma, the sum of all the vertices in sigma divided by the number of vertices. And then we add on extra terms for any other terms in x. Okay, so beta x has a term. One of the terms in it is t times Vd over d plus 1. Okay. Now, there's no cancellation because everything's positive. Okay, so that means that beta x, if you look at the coefficient of Vd, well, it's at least t over d plus 1. So in particular, strictly positive. So that means that beta x has a positive coefficient of Vd. So it's in the open star of Vd, or in other words, the open star of mu sigma hat. So that was the condition for beta for mu to be a direct simplicial approximation for beta. And then this was proposition 19.10 said that just because it's a direct simplicial approximation, that automatically means that it's a morphism of simplicial complexes, and it also automatically means that mod mu is homotopic to beta. And so it follows from that that beta inverse composed with mod mu is homotopic to beta inverse composed with beta, but beta inverse composed with beta is the identity. And similarly, if we take mu composed with beta inverse, then that's homotopic, because mod mu is homotopic to beta. This is homotopic to beta composed with beta inverse, which is the identity on mod k. So that shows that beta inverse is a homotopy inverse for mod mu, and so mod mu is a homotopy equivalence as claimed.